went back to Germany. And I'm looking forward to telling you what we're doing today. And I mean, in the best case, well, in the worst case, you have a presentation that you didn't like. And I guess in the best case, you will find common ground because I think that this is pretty complementary. I'm guessing that most of you do optimization things, more or less, right? Hi there. So what I'm working on now is a little more on how to connect systems to people, right? So how do people use algorithms? How do they interact with algorithms? How can we implement this in practice? So maybe we'll find a little bit of common ground. Ahmed and I are working together with a PhD student who was just here, Kim. I'm not sure who met Kim. All right, well, a few people did. Well, she's a PhD student of mine and my former supervisor in Germany. And I think there's a couple of interesting things. I'll talk about some of this today. So in the best case, we'll find areas where it's interesting to work together. And in the medium case, I'll just try and entertain you guys a little bit. So let's see whether I can succeed with this. So this is usually my introduction on motivating the whole thing a little bit. I'm guessing I don't need to do that for you guys because you all work in electricity or related energy fields, more or less. I'm still going to say a few things about this. So first of all, this is a tabloid article from the UK where they praise flexibility and electrification. So first of all, I think that's apparently the Brits are pretty far ahead. I think this is because they have octopus energy, but when the tabloids start praising electrification, I think that's a good thing. We're moving ahead. This is an article from the Wall Street Journal on the Netherlands, which I also find super interesting, where they talk about this guy who has a dynamic electricity tariff. And then he invites his people over for his neighbors over for coffee because he has negative electricity prices. So they all charge their EVs at his house. He makes money and they can all drink coffee together. So this is how, modern electricity, digitalized electricity systems can bring people together. And I think this is beautiful, beautiful story. This is a little bit, and we're going to move into this here and there because again, what I'm working on mostly in electricity comes from a German regulatory context, right? Regulation is very important in the electricity context. You're all aware of that. So here and there, you will get a little bit of insights of where the regulatory environment stands in Germany and in Europe. And maybe that can be interesting to kind of get ideas and see how other people do it. I know that the electricity optimization people look down on Europe from time to time because we don't have nodal pricing. We're talking about it, but I don't think it's going to get past that ever. But at least you'll get a few insights, and I think that might be interesting. So this was an article from The Verge, and they talked about this dongle thing that you could connect to digital electricity meters in Europe. And interestingly, when you go through the countries of where this can be applied, you will see that Germany is not among them because, people standardize and then Germany and Europe figures, you know what, you can all standardize, but we'll do it a little differently. So just for this motivation of, digital, how digital are we or where we are getting, what we can see is that large electricity suppliers or startups in this context, they are benchmarking themselves on the flexibility that they are contracting, right? So we're getting to a space where this becomes interesting, where they think about their portfolio, they think about who do we have under contract, how much flexibility can we get from this? And here you see a few players. Is Octopus Energy in the US as well? Is that a company that you guys know?
I would like to think yes, but I haven't.
All right. So this is a UK company that specializes in flexibility provision, right? Part of the reason why they might not be in the US is because I think in most areas in the US, you don't have free choice of supplier. In Europe, you mostly have. So you can choose who your electricity supplier is going to be, and they offer dynamic electricity tariffs, and then they pair this with heat pumps, with batteries, and so on and so forth. So this is, and they are pretty successful, and they are now moving to Germany and moving all over Europe. And then we have a few other players. I just wanted to, use that as a motivation, saying this area of flexibility is becoming more important, and people are thinking about this. And then, just very briefly, this is the German state of all of this. So often there's maps that you will not be aware of, but where we show the coverage of smart meters in Europe. And most of the countries have 100%, and then Germany has 2.5%. So this is where we stand. And this here is German for the restart of digitalizing the energy transition. if you restart something, then the original start was mostly not that good, right? So this already tells you a few things. And then we have quotes of the deplorably inadequate observability of the low voltage grid. This is what the German grid agency says, more or less the equivalent to FERC in the United States. And if these people say that we're horrible at digitalizing the grid, that says something because it's kind of their job. So that's interesting. And then if you look into the media, people are complaining that they want smart meters, but then their grid operator tells them, but your meter is in the basement and we can't connect it, and this all doesn't work. So we're moving very slowly in this regard. And so what happened recently is we start to have larger and larger spreads in the European electricity market, right? We had the gas prices. Gas is still rather expensive. Natural gas is still rather expensive in Germany and in Europe overall. So when you generate electricity from natural gas, your prices will rise pretty quickly. On the other hand, we have a lot of renewables that drive down the price to zero very frequently. So even within one day, you might have phenomenal spreads. And this was a story where we had a spread within a day of 700 euros per megawatt hour. So that's like about $800 of a spread within a day, right? This is not that electricity was expensive at some point and then later it wasn't, but that was really within a day. And the problem that we're having is that we don't have smart meters installed, so people can't really use dynamic tariffs. Not that they would necessarily accept them anyway, but that at least technically they could get them. And when we look at this story, at least what it does for me, it makes me think about, and this is the title of the presentation, of what dimensions do we have to look at when we think about this, when we think about how do we actually make the electricity system more efficient or more effective. What are the components that we need to think about? And I mean, one thing that has come up now in the discussion we had so far is regulation, right? So what kind of digital meters can you get? What kind of suppliers can you get? Who can you work with? What kind of appliances can you install? How can you operate these appliances? This plays a large role. And then this kind of goes hand in hand with behavior. Like, say I want to install a smart meter, but I'm not getting it because of regulation, then I'm not going to change my behavior. So these things are clearly interlinked, right? I have behavior and regulation that go hand in hand. And then at the same time, I have energy technologies, like, again, heat pumps. We had a large discussion after the gas crisis in Europe about how are we heating our homes in the future. And there's lots of partisan issues about this, that people say they don't want heat pumps because, I don't know, some tabloid has told them it's horrible. Again, because we're not as fast as in the UK, where the tabloid will apparently do the opposite. So what you're allowed to do and who subsidizes what, that plays a role in terms of technology and what technology is being adopted. So what has happened, for instance, across Germany, I'm not sure if you have the same trend. We have these balcony PV systems that are up to 600 watts, and you can just plug them in to your home electricity outlet. And no regulation whatsoever. And you can use this electricity, right? If you consume while it's being generated, that's fantastic. You just save on the electricity that you would otherwise have to buy. If you don't use it, it just goes into the grid, but uncontrolled, right? So everybody who's just this at their balcony now is just feeding in solar PV for free, basically, into the system. So that's pretty interesting. And again, it's an interplay between technology and regulation. I think you have Aldi here, right? Many people are not aware that Aldi is a German retailer originally, and they are selling balcony PV now. You can go to Aldi, buy balcony PV and plug it in at home. So again, regulation and technology, they go hand in hand. And then obviously technology and behavior play a large role. And I think this is what a lot of you might be working on, right? If I optimize my charging of my electric vehicle and how I have this schedule planned, how I know when I'm going to drive again, there again, technology and behavior kind of go hand in hand. And what I want to do today in the presentation is take you through a couple of things that we are working on. I mean, again, if this helps you to think about this, that would be fantastic. It helps me to think about it. And I would just kind of like to touch on a few research projects that we have at the intersections of these three dimensions. All right, let's start with the first one, with behavior and technology, because this is, and I think this is the same for you, this is the obvious thing that we think about, right? We have new technology, we have electric vehicles, we have battery storage at home, or we have battery storage in industry, and then we think about how do people deal with this now? How do they use it? What do they do? And how does that impact anything in the grid, in the system, on the market, and so on and so forth. So from an information systems perspective, we are often interested in how do people use apps. So if I give them an app and they can suddenly see how they use their electricity, what does that do to them? And this is a result from a paper where we just wanted to understand how do people perceive these apps? How do they work with them? So we surveyed people that have these kind of apps and asked them, how often do you use the app? And do you feel that you've learned more about your energy behavior? And when these squares here or these rectangles are blue, that means that they are overrepresented in terms of what we would expect. So how often have people said, I know nothing more about my energy behavior and I'm never using my app. So this is then the rectangle for this response. And given how often people have said, I don't know anything more than I knew before, or how often do I use this, then there are more people in here than we would expect just from statistics. So from just multiplying how often people said the one thing and the other, it's pretty straightforward. So anyway, what I want to say with this is these blue rectangles are overrepresented in terms of how many people fall into them. And so we can see that people who don't use the app perceive that they haven't learned anything. And the people who say they use the app a lot, they perceive that they have learned a lot. That doesn't mean that they have, but it already says something about the interaction with this, right? So we could expect if people use this more, then at least they have the perception that they get better in terms of the energy, the understanding of the energy.
So what's the meaning of the size? So you are using different square with different size. So
the size is how many people are in that overall. So when the area of the rectangle will tell you how many people fall into this category.
I see.
All right. But we're not gonna stay here. There's a bunch of things that we could explore in this context, right? Energy literacy is one thing. That's kind of the obvious thing. How much do people know about their energy consumption? Now, this is very hard to measure, to be honest. Energy literacy, there's no good survey and no standardized set of questions that we can ask people to say that they have increased their energy literacy or self-efficacy to that effect. It's a similar concept. But self-efficacy is more important in the context of when I use dynamic tariffs. Do I know how to react? What do I do when the price is low? Am I aware that a good reaction would be to, I don't know, run my dishwasher, whatever, or charge my electric vehicle? I mean, this is my perspective. I'm not sure if you share it, but this whole household energy optimization really only becomes interesting when you have more electrification. I know in the US you have a little more because most houses have air conditioning. So we have this kind of flexibility that we can use. In Europe, that doesn't exist to the same extent, but with heat pumps and electric vehicles, that will be much more important, and people will have to feel self-effective in terms of how they can react to high prices. Another interesting concept is how will people react to algorithms? We don't know a lot about this, right? How will people react when their electric vehicle is automatically charged based on dynamic tariffs, and then they go in the morning into the garage and it's not charged? What will they do? Will they opt out of the algorithm? Will they still use it? I have heard from people in the US telling me that they have this automatic optimization for their air conditioning and they are turning it off. So what do we have to do so they don't do that, right? How do we have to explain things to them? Does it have, I mean, obviously it has to be comfortable, but how often will they let it slide if it's not comfortable for that day, right? So these are all questions that we still need to answer. And then another thing that we worked on is the energy efficiency gap. Are you guys aware of this term? This was coined, I don't know, many decades ago. And the idea is, wait, let's just move on to the slide. It's coming up anyway. So the idea is, you don't have to read this. I have this summarized. Here we go. The idea is there's energy efficient technology. And with this energy efficient technology, you would save money. So let's say you can buy LED lighting, right? And just the cost savings that you have from the LED lighting pay for itself, right? So you basically don't pay for anything. It's money given to you. So the first assumption is this kind of technology exists. There's technology where people can replace what they have, and just replacing this will pay for itself, basically. That's the whole idea. And then what was observed is that people do not necessarily do this, right? So we would expect a certain amount of adoption, and we cannot see this amount of adoption. And then this is hard to explain. And this is what the energy efficiency gap describes. either these future savings are heavily discounted, like I'm saving in the future, but this future savings not worth a lot to me right now, and I would rather not invest. Maybe this is one explanation, and there's a bunch more. So when this is a problem, then we have to ask ourselves, can we address this somehow? Can we do anything? Can we have a digital intervention that would help people, or help is maybe a strong word here, but would overcome this energy efficiency gap so that energy efficient technology has a stronger market adoption quicker. And we did an experiment on this because we figured, information systems can play a role here, because this can be an information problem, right? The salience of information, maybe people just don't really know. It's a complex field. Do I want a heat pump? Do I want a gas boiler? What do I really have to do? What does one thing mean? What does the other thing mean? So if it's a question of information saliency, then information systems can play a role. And in the past, it has been shown that this has sometimes worked, like the use of labels. Like when you buy a new dishwasher or anything, you might have this. Do you have the same thing, like an energy efficiency label in the US? Like this is A, B, C or something? Yeah. So this has been shown to be successful. So I figured, maybe why don't we try this? Why don't we work on this? And so we devised an online experiment to figure out whether this had an impact. And it should come up here. So this is the experiment that you see here. This is the treatment condition, right? You would see how much electricity costs you had. What you were supposed to do is count the P's in this text field, and then you were able to turn the light on down here. When the light was turned on, you had electricity costs, and then these would increase, and here they were measured. Now I stopped counting, and here you didn't see it. You didn't see your current electricity costs. Now this is, I'm guessing, can I see it? Yeah. If you go very close, you can still read it. So you can do this task without using electricity, without using energy. You just have to move very closely to the screen. But I'm telling you, I programmed this. The RGB values are different. So one is black, the other one is not quite black. So this was possible to do. And what we wanted to understand is, how do people react? So they did this for 10 tasks, and then they had an investment choice to make. They could invest in energy efficiency, then the price would rise, or the costs would rise lower. So every second of energy use would be cheaper than it was before. And this was the same for both, right? So these people did 10 tasks. After 10 tasks, we told them, this has been your electricity costs so far. Do you want to invest? And it was the same thing here. But these people saw in every task what their current costs were, and these people only learned it after 10 tasks, right? This is how it worked. We did an online experiment. This is how, I already explained this more or less. Obviously, then you have a debriefing, you have an introduction. There was a test round that people would understand what is coming. And we collected a bunch of data on everybody. We did 2 experiments. I'll get to why we did 2 experiments in a second. In the first round of the experiment, the energy cost per second were a little higher than the second. That's not that important. The important thing is the investment costs in the first experiment were fixed. It was 20 monetary units for everybody, right? So regardless of how much electricity you had used, it was 10 monetary units for everybody. In the second experiment, it was related, the investment costs related to how much electricity you had used so far, in the sense that you would exactly break even when if you had invested for the first 10 tasks. The reason was that, I'll come to the reason in a second. I'll show you on a picture that's easier. There was a budget. They had 300 monetary units. We did this on a platform that's called Prolific. It's a British sampling platform that you can use. And that's why it translates to British pounds, because they pay people out in British pounds. There was a penalty for errors because we didn't want people to just try, right? And then, so they had 1 error for free basically per task. But then if they erred for a second time, they got a penalty. We talked about the treatment group, and we talked about when everything was shown. So let me get to the results. So what you see here on the left side. So the left side was the first experiment. I talked about the fact that this fixed investment costs was a problem, right? More or less. What we see here is on the left side, you can see how much people had, how much electricity time they had used after the 10 tasks when they had to do the investment decision. The light blue field tells you whether they invest. If they didn't invest, these are these people, and the dark blue line, these are the people that did invest. So what you can see is those invested that just used a lot more electricity, right? So this is, I mean, this is quite of an obvious result. And this is regardless of the treatment. I mean, we can see there's a slight reduction here, right? So people that were in the treatment invested a little bit earlier. It's slightly lower, but that's nowhere statistically significant or anything. So what this means here is there is no energy efficiency gap in this experiment, right? People, well, I mean, there were a few people that when I looked at all the 400 that did the experiment, there were a few people that invested even though it didn't pay for them for the first 10 rounds, probably to have peace of mind or something like this. But what we see here, this is, I mean, the unfortunate result, we couldn't identify a significant energy efficiency gap here. Now, you might say, or I will say, well, maybe that was to be expected when we did the experiment, because it's very, we talked about saliency earlier, right? This is very salient. People knew exactly how much they had paid. They knew exactly how much they would have to pay for the investment. So they could pretty easily calculate whether it would be worth for them to invest or not. That's why we did the second experiment, where midway we said, well, it's regardless, you would have come out just at zero if you had invested or had not invested, right? Would have been the same. And what we can see there, that the treatment is very effective. So in this experiment, those people that did get the treatment, so saw their electricity costs at all time, invested at significantly lower used values at the midpoint. So this is quite interesting. We didn't necessarily find an energy efficiency gap, but we did find that if you tell people in real time their costs, they are more likely to try and invest in energy efficiency. Probably because, you know, this stressed them out, because they were seeing, oh no, more costs, more costs, more costs. So then they invested so that this would increase slower, right? So this was interesting enough. Again, this has to be taken to the field, and this is what we're working on. So sorry, that was the wrong direction. Oh yeah, go ahead, sure.
So in the experiment one, what if you change the number of runs from 10 to, let's say, 100? How would that change the results?
I think it wouldn't change the results. I mean, it would be horrible for people to do that 100 times, but I don't think that would necessarily change anything. I mean, in the end, it's the same thing, right? People can calculate. At the midpoint, they can say, then I would do the investment choice after 50 rounds, right? And after 50 rounds, they would still say, well, this was my cost so far. This is how much it costs me to invest. Oh, sorry. This is how much it costs me to invest. So it would probably be the same. I wouldn't expect any change in more rounds. Actually, we did a pre-test for this experiment, and there we had more rounds, and then we shortened it because it was horrible for people. I mean, if you have to, it's not a fun task to do this, which is the whole point, right? It's not supposed to be fun. It is supposed to feel like work, and then the idea is that they can make their work easier with electricity, right? This is the kind of the simulated idea. Other question? All right. We just check the time for a second. Right, now you can lean back for a second. There's some, wait, that doesn't. Fail to detect your microphone. Yeah, well, that's fine. Oh. Here we go. So we're working on this, on bringing this into the field. We have actually built an electricity monitoring app that we're using ourselves. We have had this in the field, people tested. Yeah, sorry, this is all in German here, but this is just to show you what it looks like more or less. So we can install this with German households pretty quickly. And there I have a little fun fact in between. So here you see this kind of weird prototypically looking German guy, and you might think, what is this person doing with this flashlight? Well, the truth is, what he is doing is he's sending Morse code into a digital electricity meter to unlock some of the capabilities that it has. So that's why the smart meter rollout in Germany is very problematic. And we have these digital meters that do nothing. They cannot send information. They cannot be, you cannot communicate with them, but they will have a digital interface where they will show you how much electricity you have used. They have one feature, literally one feature that is a little smart that you can use. And it's this visual interface here. So with this, through this visual interface, it constantly sends out information. And you can use this to collect the information, but to unlock these capabilities, you first have to get a code from your supplier, and then you have to Morse this code into the digital meter with a flashlight so that it gets unlocked. And so I actually did this a bunch of times in the past, standing there and trying to enable these meters. And this is what it looks like, right? So we then have a sensor that we then put on top of this visual interface, and then we can collect information from there. So this is the one feature that it has. Why it is a visual interface and not just, I don't know, USB-C, USB, whatever connection, I cannot explain this to you. I do not know. So, well, yeah, still interesting. Well, many still have these analog meters that you might have at some points as well, still in the US, I'm guessing. We can also get information from those. They usually have this disc that turns around where there's a, yeah, you have the same. No, do you have a digital meter for your electricity where you get your consumption?
I haven't seen in my apartment.
All right, in any case, somehow, somewhere your supplier will probably know how much you consume. So we have these analog things, and we have there's a sensor in that, and because there's a little line on this disc that turns around, so we can measure how often this line has passed. And we did this, we rolled this out in the field, tested with 40 households over 2 weeks, and then asked them for their self-perceived energy literacy ahead of time. And then after the experiment, it did increase significantly. So we tested this, but I'm very skeptical, and I'll show you in a second why, that this was actually because of the app and not just because for the first time somebody told them anything about their electricity consumption, right? I think this kind of is a self-perception. You then think about it, I don't know, maybe you occupy yourself with this a little more, and then you feel like, yeah, my literacy has increased. And yeah, I mean, we had a bunch of items. We didn't like ask them, has your literacy increased? But so we asked stuff like, how much do you know the cost of 1 kilowatt hours that you have, or something like this. So it did increase, but yeah, well, you know, I'm still skeptical. I'll show you why. I'll show you also why I'm skeptical. So we tried to understand whether the use had any impact on the increase in energy literacy. And this is the energy literacy difference, because the regression didn't tell us anything. I brought you this correlation plot. And what we get, so the middle is basically use. These are all use values. So if you use some features more, you will use other features more as well, right? So that's why this is there is a lot of correlation here. But what's interesting is I think these two lines, these two rows, this is the energy literacy score at the end, and this is the difference. And we see very light correlations. And if anything, it's negative correlation. So it's a little strange. We can't really, from all the data that we collected, and we collected a lot, we collected all kinds of use data of what people clicked on, how often they logged in, and what they used. We cannot really explain any increase or change in the energy literacy. So I don't know. I'm still working through this, through having learned this. This is pretty fresh, and what we will have to think about whether we need different features or anything else. So yeah, that didn't really help. In terms of the use of the app, we could explain this better. So interestingly enough, people that had a high energy literacy, self-assessed energy literacy score at the beginning used the app more, right? And again, this is significant. So, and then again, this is not a well-designed app, because we want people who feel like they know nothing to use the app and then learn stuff, right? So we're still having a bunch of problems here. This is energy worries. We asked people, how worried are you about your energy costs and stuff like this? And again, people that scored high on this were more likely to use the app more often. But then these two, well, maybe we can look this up live, whether these two are, well, no, they are not very correlated either. Okay, so that's fair enough. So at least there's some component of, if I'm worried, I'm going to use the app more. A bunch of income things. So people who have in the highest income bracket used it more. But again, this is not what we want, right? We don't want literate or people that don't have to worry about energy to use this app. We want this for other people, right? That struggle more in terms of energy consumption, so on and so forth. So anyways, right, moving on. And I've used a lot of my time, but I think now maybe at least the middle part could be a little more interesting for you, if you didn't find that part interesting so far. I'm not assuming anything. Right, so we talked about behavior and technology, right? So obviously there's an interplay. Let's talk a little bit about behavior and regulation. And again, this might be interesting. So what we were interested in understanding is, how do people use battery storage? So I'm sure you've all read paper, maybe you've even written papers on how we should optimize battery storage against the market, against the grid, against whatsoever. And there's a lot of these things out there. And we had the opportunity to kind of understand what do people actually do. So we got, oh wow, yeah, I saw this earlier. That's pretty nice. All right. Can this thing jump? You always see these videos of how Boston Dynamics developed over time. Anyways, so we got empirical profiles from 1,000 households in Germany over a year and how they use their battery storage. So this allowed us to see, well, what did this battery storage do for the system, right? And the German regulation, that's maybe important. I'm not sure what the Massachusetts regulation is. I know that in California, they had net metering for a while. Is that the same here? Yeah, so in Germany, it's self-consumption prioritized regulation. So when you consume your own electricity, that's for free. You don't have to pay anything, right? But if you feed into the any electricity you get out of the grid, you pay a lot of levies, you pay taxes, and so on and so forth, right? So you cannot feed it into the grid and then get it back. If you feed it into the grid, you get a feed-in tariff, but that's it, and that's not too high as compared to the costs. So we are incentivizing self-consumption, and our hypothesis was that this will not be good for the system overall, right? The way people use storage because of that will not help the system the way we think. So we did this evaluation and then we simulated. I'll cut this one out if you want to read it. The paper is out. This is what it looks like. So this is the cumulative income that the storage would have made on the market had it operated against the market and not for the household individually, right? And what you can see here, this is the zero line. There's a bunch of storage units that are installed in Germany that have made a loss throughout the year. And again, this loss is basically just socialized because it goes into the grid fees. Because, I mean, if these people did not have had a storage, electricity would have been cheaper for the system overall, right? So, and I have the numbers here. So on average, the system benefit of every battery storage that was installed was $5. For the individual households, it was a lot more, right? But for the system, these battery storage basically didn't do anything. And 23% were below the zero line, so they actually made a loss. And we made very small adjustments. So on what you see on the right side is that we allowed battery storage still to only charge from self-consumption. You could not charge your storage by buying electricity from the grid, but everything else was against real-time pricing. So you could sell electricity that you self-generated for the real-time price, and you could buy electricity back for the real-time price at any point in time, right? This was the only change. We didn't allow storage. There was no net metering, nothing. You couldn't get electricity from, and the storage could not even be charged from the grid. That was not allowed. You could only charge your storage from your own PV. And just this very small adjustment already led to the fact that they made about 10 times more for the system overall. Yes, please.
So what exactly was happening in the first one?
Yeah.
So,
yeah.
Okay, yeah, I assume you're going to explain it, but.
I can, yeah. Sorry, I thought there were.
Like, sorry, with the first one,
yeah.
Why? I would think that if you can't resell to the grid or you get a very low feed-in tariff, you would have you would be charging when electricity was very low priced because that's when there's a lot of solar out, and you're discharging when, I guess it could be like if there's a lot of wind or something like that, you might discharge when there's a lot of wind and the price is still cheap. But
fair point. I didn't explain that very well. Thank you. So the way the regulation currently works is you can only charge your storage from your self-generated PV. You cannot charge the storage from the grid. So what the households are doing is they are basically just charging their battery storage until it is full from their self-generated solar PV, and then they discharge it when they need electricity in their household. So there's basically no interaction with the market or the system whatsoever. It's all self-optimized. It's charged during the day when there's more PV generation in the house than what the house consumes. And then as soon as the house consumes more than the self-generated PV, the storage is discharged again. So you basically have about 280 full cycles, equivalent full cycles of the storage per year. Because if it's a good day, you charge it to 100% and then you discharge. If it's not that much of a good day, you don't charge until 100%, but that's it. So they are only optimizing against themselves. And what we did here is figuring out, well, but the way they operated, what does that mean for the market? Because it has repercussions for the market, right? Because these households potentially charge their their storage when electricity is very expensive, during a time when it would be much better if they sold their self-generated electricity to the system overall. But they don't, because they don't have an incentive for it.
So that would happen though when there's not high penetration of PV and there might be high penetration of wind or something like that.
All right, fair enough. Your argument is that in times when there's a lot of PV, the price will usually be low anyway, so it's fine when they do it. Yeah, fair enough. I mean, the penetration of PV in Germany is pretty high, and still we get to these values, right? So, but this is what people are doing. You're absolutely right. You would expect that if prices then are always low when PV is high, but and again, I mean, we can probably see this here, right? So in the summer, we see that there's not that much loss, right? It comes rather in the winter. So this is probably when there's not enough PV in the system overall. So this is when they are really losing the money against the market, because here it would be better if they would sell their PV, right?
Got it. Got it.
Explanation. Yeah.
Just a follow-up question.
Sure.
So for the left figure, so what is the y-axis? So the y-axis is the cost for the household or the cost for the system?
This is the cost for the system if you had acted this way against the market.
Okay. So
It's basically, let me frame it differently. It's basically the profit of the storage. It's the profit of the storage against the market.
Oh, I see. Oh, I see. I see. Okay.
So we might expect a graph, or we might expect a similar pattern in Massachusetts, which has maybe a more similar environment to Germany compared to California or Texas.
Yeah.
Just hypothetically.
Absolutely. Yeah, that's very probable. Like if you see the duck curve in California and so on and so forth, we might expect, and since, you know, there is sun throughout the year, so yeah, it's probably not, it wouldn't have the same effect, probably. But again, it would not have this, the problem here is that it's not aligned, right? From a regulatory perspective, it's just not well aligned with the market. In California, by lucky accident, we might see a different pattern. It's still not a good regulation, I would argue. This would be my argument, right?
And if you moved in the other direction towards complete net metering, it might be even worse.
Well, in that case, nobody would install storage, right? This is always the problem.
Yeah.
Exactly. Yeah. All right.
One question.
Yeah, sure. No.
So could you maybe just talk about PV here, because it affects this figure, I guess. So like, what is the sizing of the PV that you assume? Because if the PV is oversized, then maybe the battery is.
That's a good question. To be honest, I cannot even tell you. I don't have an answer for this, because we got the data for the storage. We also know how big the storages are that we have here. But don't ask me, because I don't remember, but it's in the paper. I can look it up for you if you want. But we have no idea of how large the PV actually is. But what we can tell you with the data that we have is how often the storage gets to 100%. So I'm guessing this gives you an idea of how large the PV is sized, roughly. Yeah. All right. Okay. I think that's it for this. So anyways, the point again being that regulation impacts behavior, right? What you do depends on the incentive system that is being built for you. And then this incentive system needs to be carefully designed, because the thing is, if this is 1,000 storage units that we looked at, maybe that's fine. But if this is 2 million, 3 million, 4 million storage units that act this way against the market, then we're running into trouble. And I mean, obviously, this was a sample. This is not all the storage units that are being installed. All right, let's move into the last aspect, and I think this is the most abstract. It was the most abstract for me when I started working on this, because it's a little more, how to say, it's qualitative. Let's just say this. So how does regulation and technology interact? And I'm still going to use this opportunity to just tell you a few things about what we're currently thinking about, because this is what we're working on with Kim as well. The so-called famous, at least in Germany, famous parable 14a. So in terms of regulation, maybe just start a little bit with how can I regulate? But in the US, in the UK, lots of law is basically common law, right? So I have precedents and something has been decided, and then I refer back to these precedents. And I'm trying to work along an architecture, a legal architecture that is building over time. And please don't pit me. I'm not a legal expert or legal scholar. I have no idea what I'm talking about right now, but I'm doing my best. I'm doing the best that I can. And basically, what I'm telling you here now is from the book from Richard Brown's work, where he explains these different paradigms of how you want to regulate. So this would be, there's a new technology, there's AI, and I have legal doctrines and principles, and then AI comes into the picture. So I judge AI along the lines of what I already have, right? There is an idea of the law, and this applies obviously to new technology as it has applied to older technology. And this is how I then think about things. Then, at least the way he frames it, you have Law 2.0 that goes one step further, where I think about new technology coming in, and I believe that my current framework of the law is not sufficient to regulate this new technology. Think EU AI Act, right? So I have new technology, and I think about what regulation I would maybe need for this technology to work as ideally or work positively for society, let's say it that way. And then what he coins, and this is the interesting part that I want to talk about, is Law 3.0, where we no longer think about regulating things and giving out rules and saying, yeah, but you have to abide by the rules, and we enforce regulation by X, Y, Z, but technology basically enforces regulation. Right? One common example for this is a speed bump. There's a speed bump on the road, you're not supposed to speed wherever it is, and you're not going to speed, because if you run over the speed bump too fast, you're gonna damage your car. Another more technological example is in the airport. When you leave the airport, when you leave the plane towards baggage claim, you go through these doors that only open in one direction, and if you want to go back, you can't, right? So this secured area is cannot be accessed in the other direction, right? It's an architectural approach to enforcing regulation. Why am I telling you this? So I'm sure you have the same challenges here in the US. With an electrified distribution grid, we get in trouble because we don't have a lot of visibility in the distribution grid, and we suddenly have much larger electrical loads in the distribution grid, right? If we have an 11 kilowatt charging station at every household, this becomes a challenge for distribution grids. Either I reinforce them, or I start doing things like smart charging control, or I shed certain loads if I have to. And this is what Germany has thought about, right? So we have a lot of electrification in the distribution grid, and the question was, what do we do? So this paragraph was devised, the paragraph 14.8, and it describes that when you buy an appliance or an electrical consumer that has a certain size, which is basically heat pumps, battery storage, and electric vehicle charging, then you need to register those, and they can be dimmed. So the electricity they consume can be dimmed at any point in time. That the minimum, I mean, that's the German regulation, it's not that important. It's 4.2 kilowatts. So you will always be allowed to have consume 4.0 kilowatts per this type of appliance. Do you guys have a better word when I say charging stations? Are these appliances? Okay, I'll call them appliances. Fine. So every such appliance still gets awarded at least 4.2 kilowatts, but it can be reduced to that, right? Then you cannot consume more than this minimum. And this law or this regulation was enacted over a long period of time, right? So first there was a law on that we want digital meters and this cyber-physical electricity system. Then they defined what these appliances were exactly. Then there was a first draft, then there was a second draft, and there was a whole consultation process throughout this time where people could complain or, I don't know, try and get their interests through. And it was pretty interesting because you can see, I don't know, these kind of institutional tussles is what it's called, right? So people with different interests from different institutional backgrounds come in and have certain interests. So the electric vehicle industry was heavily against this. So, and because the car industry in Germany is a very strong political actor, this law, for example, this law was completely scrapped. They basically said, we're not going to do it. And then they passed it on to an agency so they don't have to take legislative action. And I think this is kind of, again, similar as to what we sometimes see in the United States. And so what we started doing is kind of analyzing this to better understand what role does technology play here in this whole idea of regulating things through technology instead of enforcing it through agencies or through control or anything like this. Because what has happened is basically people just can't consume more, right? You don't have a choice. You can't not abide by the rules, right? It's not possible for you. And so we analyzed what kind of technology, what the role of technology here is, and we have 4 categories that became interesting in this context. And I think this might still be interesting also from a global perspective. So one is communication architecture. How do you communicate? Because you need to connect all of these very individual appliances now suddenly to your grid control stations, right? Somebody needs visibility. These people suddenly need to know exactly at what point in the grid they have which resources that they can use. And so in Germany, we have about 800 DSOs. Not sure how much you have in the United States, but I think you also have a bunch, maybe not that many. But the thing is, they all need to work on the same standards, because also the appliance producers need to work on the same standards, right? Everybody needs to be able to talk to each other. And over time, over this period, when they started designing this law, it's interesting that in the beginning, they didn't really understand that standardization was an important topic in this context. Another point is grid state evaluation. What is actually the state of the grid? When am I going to need to dim the electricity consumption of these appliances? Because that's not always entirely clear, because there's very little visibility. When do I even know that there is going to be congestion in this grid? How do I learn this? Right? I need sensors then, and these sensors need again to be very distributed. So what they are also thinking about is how do I have a sensor at every transformer? Do I have a sensor at every household? Do I have a sensor at every appliance? Like, how do I distribute this? And there's a lot of machine learning in this as well, to kind of figure out what's the minimum number of sensors that I can install to know everything about my system, right? So that I can infer from the sensors that I have there. And then what we see, and I mean, I guess this is not ideal because there was not a lot of experimentation. They're just getting stricter and stricter across time. Then how do you document all of this, right? How do you know that there was a congestion? So they talked about how they use technology for this. And then what is the role of the customer? How can the customer still optimize, right? In these laws, they talk about energy management systems. How does the customer optimize against these constraints that he's getting? If I tell you, well, later today, I'll reduce your consumption, but then you don't really know because you're doing that when the congestion comes in. So how do customers react when the constraint is lifted? Is then everybody going to charge at the same time? This could be a problem again. And the one big problem in this whole context is that customers do optimize, because if you have dynamic tariffs and you have cheap electricity, what is every electric vehicle going to do? They are all going to charge at the same time. And then you get this distribution grid congestion, right? So you really need to think about how you optimize consumers in this context. So again, I know qualitative, but I think this holds a lot of interesting lessons to think about. Where is research going in terms of technology, in terms of algorithms, in terms of what do we need to do? How do we need to think about behavior? And a bunch of these things we have said for years, right? Like these waterfall effects that people start charging all at the same time. This is not necessarily new, but now it comes into practice, and we need to think about how to deal with this and how to regulate it, or not, well, or incentivize, right? I've talked a lot about regulation now in terms of command and control. I mean, we can also incentivize people and then maybe we need some type of nodal pricing on a distribution system level, right? But we need to implement it, we need to communicate it, we need people to react to it. And I think there's a lot of interesting challenges in this. All right, that's it for me. Thank you very much. I hope that I've convinced you that this is interesting, this whole digitalization triangle. There's a little bit of a conclusion, and if you still have questions, I'd be happy. Oh, sorry, it's all a little slow to take them. Thank you.
Yeah, I had two questions. The first was, I missed whether that was like the registration of heat pumps and similar devices. Is that something people are thinking about or people have done?
That's done. That's implemented. So everybody who installs anything that is classified as it's called a controllable appliance, then you have to register with your DSO. In turn, the DSO, and this is what they gave to the consumers on the other hand, is that the DSO cannot say no. If you want to install a heat pump or you want to install an electric vehicle charger, the DSO cannot say, well, but we don't have the capacity. You can install it immediately. You just have to tell them, and it has to be controllable.
And do you think that that type of requirement would be possible in the United States, where there's a lot of, I think there's more emphasis placed on privacy?
Yeah. Oh, good question. I mean, so the whole idea about that was one of the problems with the whole smart metering thing in Germany, that they kind of put privacy very high on the agenda. So these appliances that they built were very, at least at the time when they were first thinking them up, very cyber secure. But because of that, they became very, very expensive, and that slowed down the whole rollout. Would that be, I mean, I guess you're the expert. To be honest, I can't tell you. I'm not sure whether this is a privacy issue, this controllable thing. If I had to say anything about the American psyche, I would rather think that it could be a problem because you're kind of limiting freedoms, right? So if I want to charge my electric vehicle, I want to charge my electric vehicle. And we had that discussion in Germany as well. I mean, but it's a pragmatic thing in the end, right? If everybody charges their electric vehicle and the grid breaks down, then everybody loses, right? So somehow you need to find a pragmatic solution, I'm guessing. Germany has proposed this one. I think it's interesting enough to think about it, but I would never say that this is the best idea. I think there's other better ideas, to be honest. I think working with incentives that are then being translated to energy management systems, and then this is somehow distributed. We're not very good at digital in Germany. So I think maybe this is rather the way for the world to go, right? To really make sure that the right economic signals are being sent to these appliances, something like that. Yeah. You had another question? Or
No, those were my two.
Thanks.
Yeah.
All right.
I have a question.
Yeah, sure.
Very interesting.
Thank you.
So